Azure IAM for AWS power users. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. If you're an AWS power user looking to expand into Azure, understanding identity and access management is critical. While both platforms solve the same fundamental problem of controlling who can access what resources, they approach it with different philosophies and terminologies. Azure's IAM system is built around Microsoft's enterprise heritage, particularly Active Directory, while AWS developed its IAM independently with a focus on programmatic access and fine-grained policies. This presentation bridges the gap between these two worlds. We'll map AWS IAM concepts directly to their Azure equivalents, highlight key differences in architecture and approach, and provide practical guidance for managing identities and permissions in Azure when you're already familiar with AWS patterns. The goal is to accelerate your Azure learning curve by leveraging your existing AWS knowledge. We'll start by comparing the high-level architecture of both IAM systems, then dive into specific components like users, groups, roles, and policies. You'll learn how Azure's subscription model affects permissions differently than AWS accounts, understand the distinction between Azure AD and traditional IAM, and discover where Azure provides capabilities that AWS doesn't have natively, and vice versa. Identity Management Philosophy. The fundamental difference between AWS and Azure IAM starts with their philosophical approaches to identity management. AWS IAM was designed as a standalone service focused on API access control. Every AWS account has its own IAM service, creating isolated identity silos. Users and roles exist within a single account, and cross-account access requires explicit trust relationships and role assumption. This model prioritizes security through isolation but requires additional work for multi-account organizations. Azure took a different path, building on Microsoft's decades of enterprise identity experience with Active Directory. In Azure, identity is centralized in Azure Active Directory, which exists outside and above your Azure subscriptions. This means a single identity can seamlessly access resources across multiple subscriptions without role switching or temporary credentials. Azure AD is the identity plane, while subscriptions are the resource plane, creating a clean separation of concerns. This architectural difference has profound implications. In AWS, you might create separate IAM users in development and production accounts, managing them independently. In Azure, one person has one identity in Azure AD that can be granted different permissions in different subscriptions. This reduces identity sprawl but requires careful planning of your Azure AD tenant structure. The diagram on the slide illustrates this key difference. AWS shows three separate accounts, each with its own IAM service containing users, groups, and roles. Cross-account access requires role assumption with temporary credentials. Azure shows one Azure AD tenant at the top, containing all identities, with multiple subscriptions below. The same user identity flows down to all subscriptions without requiring separate credentials or role switching. This single sign-on capability across subscriptions is built into Azure's architecture from the ground up. Another important distinction is how these systems handle human versus machine identities. AWS uses IAM users for people and IAM roles for applications. Azure uses Azure AD users for people and service principals or managed identities for applications. Both approaches work, but Azure's managed identities provide automatic credential rotation and lifecycle management that AWS IAM roles don't offer natively. Core IAM Components Comparison. Let's examine the core building blocks of IAM in both platforms and how they map to each other. Understanding these equivalencies is essential for translating your AWS knowledge to Azure. In AWS, an IAM user is an entity representing a person or application with long-term credentials. The Azure equivalent is an Azure AD user for people or a service principal for applications. The key difference is that Azure AD users are centralized across your entire organization, while AWS IAM users exist only within a single account. When you need programmatic access in Azure, you create a service principal rather than giving applications user credentials. AWS IAM groups are collections of users that share common permissions. Azure has two equivalents: Azure AD groups for organizing users and Azure AD security groups for permission assignment. Azure's groups are more powerful because they support dynamic membership based on user attributes. For example, you could automatically add all users with the job title developer to a developers group without manual intervention. IAM roles in AWS are identities that can be assumed by users, applications, or services to gain temporary credentials. Azure's equivalent is also called roles, but they work differently. Azure roles are permission sets that you assign to identities at specific scopes, like a subscription or resource group. You don't assume an Azure role. Instead, you're directly assigned that role's permissions. For temporary elevated access, Azure uses Azure AD Privileged Identity Management instead of role assumption. The table on the slide provides a comprehensive comparison of these components. Notice how AWS IAM policies map to Azure role definitions. Both define what actions are allowed or denied, but Azure's role-based access control model means you assign roles rather than attaching policies. AWS has inline policies and managed policies. Azure similarly has built-in roles and custom role definitions. One component unique to AWS is IAM instance profiles, which attach roles to EC2 instances. Azure's managed identities serve the same purpose but are more sophisticated. A system-assigned managed identity is automatically created and managed by Azure, tied to the lifecycle of the resource. User-assigned managed identities can be shared across multiple resources and managed independently. Both eliminate the need for storing credentials in your code. Resource-based policies in AWS allow resources like S3 buckets to define who can access them. Azure has a similar concept called resource policies, but they're less commonly used because Azure's RBAC model handles most access control scenarios. The Azure equivalent is typically implemented through Azure RBAC assignments at the resource scope rather than policies attached to the resource itself. Permission model architecture. The way permissions are evaluated and applied differ significantly between AWS and Azure, and understanding this difference is crucial for effective access management. AWS uses a policy-based model where you attach JSON policy documents to identities or resources. These policies explicitly list allowed or denied actions using the action element. When multiple policies apply to a request, AWS evaluates them all and uses a deny by default approach with explicit denies taking precedence. Policy evaluation considers identity-based policies attached to the user or role, resource-based policies attached to the target resource, service control policies from AWS, organizations, and permissions boundaries. Azure uses a role-based access control model built on role assignments. A role assignment connects three things: a security principal, who gets access, a role definition, what they can do, and a scope, where they can do it. Instead of writing JSON policies, you typically assign built-in roles like owner, contributor, or reader. These roles are collections of permissions that make sense together. You can create custom roles if the built-in ones don't meet your needs. Let's walk through the sequence diagram to see how permission evaluation works in both systems. In AWS, shown in the top sequence, a user makes a request to access an S3 bucket. AWS IAM first checks if there's an explicit deny in any policy, whether identity-based, resource-based, or organizational. If there's a deny, access is immediately rejected. If there's no deny, IAM checks for an explicit allow in any applicable policy. If there's an allow, access is granted. If there's neither an explicit deny nor an explicit allow, the request is denied by default. This means permissions must be explicitly granted. In Azure, shown in the bottom sequence, a user requests access to a storage account. Azure RBAC first gathers all role assignments that apply to this user at this scope and all parent scopes. Subscription-level permissions flow down to resource groups and resources within them. Azure then combines all the permissions from these role assignments. Unlike AWS, Azure uses an additive model where permissions accumulate. If any role assignment grants the needed permission, access is allowed. There's no concept of explicit deny in standard Azure RBAC, although Azure AD Conditional Access can block access based on conditions. A critical difference is scope inheritance. In AWS, permissions don't automatically flow down organizational units to accounts. In Azure, role assignments at a subscription level automatically apply to all resource groups and resources within that subscription. You can be assigned reader at the subscription level and automatically have read access to every resource in that subscription. This inheritance makes Azure permissions more powerful but requires careful planning to avoid unintended access. Another important concept in Azure is the management group hierarchy. Management groups sit above subscriptions and allow you to assign roles at an organizational level. If you assign someone contributor at a management group, they get contributor access to all subscriptions under that management group. This is similar to AWS organizations' SCPs but with an allow model rather than a deny boundary. AWS IAM Deep Dive. Before we dive into Azure specifics, let's ensure we have a solid understanding of AWS IAM's structure. This serves as our reference point for comparison. At the top level, you have an AWS account, identified by a unique account ID. Within this account, the IAM service manages all identities and policies. IAM users represent individual people or applications with permanent credentials. These users can have console passwords for web access and access keys for programmatic access. Best practice is to avoid using the root account for daily operations and instead create IAM users with appropriate permissions. IAM groups simplify permission management by allowing you to organize users logically. Instead of attaching policies to each user individually, you attach policies to a group and add users as members. A user can belong to multiple groups, and they inherit permissions from all groups they're members of. This makes onboarding and offboarding efficient since you just add or remove group memberships. IAM roles are the most powerful feature in AWS IAM. Unlike users, roles don't have permanent credentials. Instead, they define a set of permissions in a trust policy that specifies who can assume the role. When an entity assumes a role, AWS Security Token Service issues temporary credentials valid for a specified duration. This is how cross-account access works in AWS, how EC2 instances get permissions, and how you implement least privilege through just-in-time access elevation. The architecture diagram shows these relationships clearly. At the top is the AWS account container. Inside, we have IAM users, each potentially belonging to one or more IAM groups. Groups have IAM policies attached that define permissions. Users can also have policies attached directly, though this is generally discouraged. IAM roles sit separately, with their own attached policies and trust policies. EC2 instances use roles through instance profiles, and external identities can assume roles through federation. IAM policies are JSON documents containing one or more statements. Each statement specifies an effect allow or deny, one or more actions like S3:get object, resources identified by ARNs, and optionally conditions that must be met for the policy to apply. There are identity-based policies attached to users, groups, or roles, and resource-based policies attached to resources like S3 buckets. Policy evaluation in AWS follows a specific order. First, all applicable policies are identified, including identity-based policies, resource-based policies, IAM permissions boundaries, AWS organizations SCPs, and session policies. Then, Explicit denies are checked across all policies. If any policy has an explicit deny for the action, the request is immediately rejected. If there's no explicit deny, AWS checks for explicit allows. If at least one policy allows the action and no policy denies it, the request is granted. If there's no explicit allow, the request is denied by default. Azure AD and RBAC architecture. Azure's Identity and Access Management System is fundamentally different from AWS because it separates identity management, Azure AD, from authorization, Azure RBAC. Understanding this separation is key to mastering Azure permissions. Azure Active Directory is Microsoft's cloud-based identity and access management service. It exists independently of your Azure subscriptions and can even be used without any Azure infrastructure subscriptions at all. Azure AD manages users, groups, service principals, and managed identities. It handles authentication, proving who you are, through various methods including passwords, multi-factor authentication, certificate-based authentication, and federated authentication with on-premises Active Directory or third-party identity providers. Once authentication succeeds through Azure AD, authorization is handled by Azure RBAC at the subscription and resource level. This is a crucial distinction. Azure AD says, "Yes, this is John Smith," and Azure RBAC then checks, "What is John Smith allowed to do in this subscription?" You can have an Azure AD account without any Azure resource access, and you can't access Azure resources without an Azure AD identity. The architecture diagram illustrates this layered approach. At the top is the Azure AD tenant, your organization's dedicated instance of Azure AD. Inside the tenant are users, representing people, groups, collections of users, service principals, application identities, and managed identities, Azure Managed Application Identities. Below the Azure AD layer is the management group hierarchy, which provides organizational structure for your subscriptions. Management groups allow you to organize subscriptions into a hierarchy for unified policy and access management. The root management group sits at the top, and you can create a tree structure beneath it with up to 6 levels of depth. When you assign an Azure role at a management group, that assignment cascades down to all subscriptions, resource groups, and resources within that management group's scope. This is powerful for implementing organization-wide governance. Subscriptions sit within the management group hierarchy. Each subscription is a billing and resource container. Within a subscription, you create resource groups, which are logical containers for related resources like virtual machines, storage accounts, and virtual networks. At the bottom are the individual resources themselves. Azure RBAC role assignments can be made at any level of this hierarchy: management group, subscription, resource group, or individual resource. The principle of scope inheritance means permissions granted at a higher level automatically apply to all lower levels. Let's trace a typical access scenario. A user authenticates to Azure AD using their credentials and possibly multi-factor authentication. Azure AD verifies their identity and issues a token. When the user tries to access a resource, Azure RBAC checks all role assignments for that user's identity directly or through group membership at the resource scope and all parent scopes up to the root. If any role assignment grants the necessary permission, access is allowed. If no role assignment grants the permission, access is denied. Service principals and managed identities deserve special attention. A service principal is an identity for an application, hosted service, or automated tool that needs to access Azure resources. You create a service principal in Azure AD, generate credentials for it, and then assign it Azure roles just like a user. However, managing service principal credentials is your responsibility. Managed identities solve this problem by having Azure automatically manage the credentials and rotate them. System-assigned managed identities are tied to the lifecycle of a single resource, while user-assigned managed identities can be shared across multiple resources and managed independently. Scope hierarchy and inheritance. One of Azure's most powerful features, and one that differs dramatically from AWS, is the scope hierarchy and how permissions inherit through it. This system provides tremendous flexibility but requires careful planning to avoid unintended access. At the top of the hierarchy is the root management group, which is automatically created for your Azure AD tenant and encompasses all subscriptions. You cannot delete or move this root group. It serves as the ultimate parent for your entire Azure organizational structure. This is conceptually similar to the root of an AWS organization but with different permission behavior. Below the root, you create custom management groups to reflect your organizational structure. You might have management groups for different business units, environments, for example production, staging, development, or geographical regions. Management groups can be nested up to 6 levels deep, allowing complex hierarchies. For example, you might have a top-level management group for a business unit, child management groups for each environment, and subscriptions within each environment group. Subscriptions are the next level down. Each subscription is a billing boundary and a resource container. Large organizations often have many subscriptions separated by purpose, environment, or department. Unlike AWS accounts, which are somewhat heavyweight, Azure subscriptions are lightweight and designed to be used in multiples. A user's identity doesn't exist within a subscription. It exists in Azure AD and is granted access to subscriptions through role assignments. Within a subscription, you organize resources into resource groups. A resource group is a logical container for resources that share the same lifecycle. For example, all resources for a web application might go in one resource group so you can manage, monitor, and delete them together. Resource groups cannot be nested. They're a flat organizational structure within a subscription. Finally, at the bottom are individual resources like virtual machines, storage accounts, databases, and networks. These are the actual Azure services you deploy and use. The critical concept is scope inheritance, illustrated in the diagram. When you assign an Azure role at a scope, that assignment automatically applies to all child scopes. If you assign someone the reader role at a management group level, they automatically get reader access to all subscriptions under that management group, all resource groups in those subscriptions, and all resources in those resource groups. They don't need separate role assignments at each level. The diagram shows this with a user assigned the contributor role at the subscription scope. The green checkmarks indicate where this role assignment grants access. Because the role is assigned at the subscription level, the user automatically has contributor permissions on resource group A and resource group B, and on all resources within those groups: virtual machine 1, storage 1, virtual machine 2, and database 1. If you wanted to restrict access, you would assign the role at a lower scope, such as only on resource group A. This inheritance model differs from AWS, where permissions don't automatically cascade. In AWS, granting access to an account doesn't automatically grant access to resources within that account. You must explicitly grant resource-level permissions. In Azure, granting access at a higher scope inherently grants access to lower scopes unless you implement deny assignments, which are rare and typically used only through Azure blueprints or system features. Best practice is to assign roles at the highest scope that makes sense for the permission level needed. If someone needs read access to everything in a subscription, assign reader at the subscription level. If they need write access only to resources in a specific resource group, assign contributor only to that resource group. This principle of least privilege combined with scope inheritance makes Azure permissions both powerful and efficient. Built-in roles versus custom roles. Azure provides dozens of built-in roles covering common permission scenarios, but you can also create custom roles when needed. Understanding when to use built-in versus custom roles is important for maintaining security and manageability. The 4 fundamental built-in roles in Azure are owner, contributor, reader, and user access administrator. These roles exist at every scope level and cover the majority of access scenarios. Let's examine each one in detail. The owner role grants full access to all resources and the ability to assign roles to others. Someone with owner at a subscription level can create, modify, and delete any resource in that subscription and can grant permissions to other users. This is the most privileged role and should be limited to a small number of administrators. It is equivalent to combining AWS's administrator access policy with the ability to manage IAM. The contributor role grants full access to manage all resources but cannot assign roles to others. This is perfect for developers and operators who need to work with resources but shouldn't manage access control. A contributor can create virtual machines, modify storage accounts, deploy applications, but cannot grant another user access to those resources. In AWS terms, this is similar to power user access without IAM permissions. The reader role grants read-only access to view all resources but cannot make any changes. This is ideal for auditors, support staff, or anyone who needs visibility without modification rights. Readers can see configurations, read logs, view metrics, but cannot create, update, or delete resources. This is similar to AWS's read-only access managed policy. The user access administrator role is unique. It grants the ability to manage user access to Azure resources but not to manage the resources themselves. Someone with this role can assign roles to others, view role assignments, and manage access, but cannot create a virtual machine or modify a storage account. This separation of duties is powerful for security teams who need to control access without touching infrastructure. Beyond these foundational roles, Azure provides hundreds of service-specific built-in roles. The table shows some common examples. The virtual machine contributor role can manage virtual machines but not the network or storage they use. The storage blob data reader can read blob storage data but cannot manage the storage account configuration. The network contributor can manage network resources. The SQL DB contributor can manage SQL databases but not access the data within them. These specialized roles follow the principle of least privilege by granting only the permissions needed for specific job functions. When possible, use these service-specific roles instead of the broader contributor role. For example, if someone only needs to manage virtual machines, assign virtual machine contributor rather than contributor. This limits their ability to accidentally or maliciously affect other resource types. Custom roles become necessary when built-in roles don't match your requirements. You create a custom role by defining a JSON role definition specifying which actions are allowed or denied. Each action corresponds to an operation in an Azure resource provider, like Microsoft.compute/virtual-machines/start/action or Microsoft.storage/storage-accounts/read. You can start with a built-in roles definition and modify it, or create one from scratch. When creating custom roles, be specific about assignable scopes. You can limit where a custom role can be assigned, such as only to a specific subscription or management group. This prevents the role from being used in unintended contexts. Also, maintain clear documentation for custom roles including their purpose, who approved their creation, and why built-in roles were insufficient. Custom roles add complexity, so use them sparingly and only when necessary. Service principals and managed identities. One of the biggest operational differences between AWS and Azure is how you handle application identities and credentials. Azure's managed identities provide capabilities that AWS doesn't natively offer, eliminating entire classes of security problems. In AWS, when an application needs to access cloud resources, you typically create an IAM user with programmatic access, generate access keys, and configure your application with those credentials. For EC2 instances, you use instance profiles with IAM roles to avoid storing credentials. For applications outside EC2, you're back to managing access keys, which must be rotated, stored securely, and can be leaked. Azure provides two identity types for applications: service principals and managed identities. Understanding when to use each is important for security and operational efficiency. A service principal is an identity for an application or service that you create in Azure AD. It's analogous to an AWS IAM user for applications. After creating a service principal, you can generate a client secret like an AWS access key or use certificate-based authentication. You then assign Azure roles to this service principal just like you would to a user. Your application authenticates to Azure AD using the service principal credentials and receives a token to access Azure resources. The challenge with service principals is credential management. Client secrets expire and must be rotated. If secrets are compromised, you must revoke them and update all applications using them. Storing secrets securely in Azure Key Vault or AWS Secrets Manager adds complexity. Certificate-based authentication is more secure, but adds certificate lifecycle management overhead. Managed identities solve these problems through automation. When you enable a managed identity for an Azure resource like a virtual machine, app service, or Azure function, Azure automatically creates a service principal in your Azure AD and manages its credentials. Your application code requests a token from the Azure Instance Metadata Service, which handles authentication behind the scenes. The credentials are automatically rotated, never exposed to you, and cannot be accidentally leaked because you never see them. Let's walk through the sequence diagram showing how managed identities work. First, you enable a system-assigned managed identity on an Azure virtual machine. Azure automatically creates a service principal in your Azure AD linked to that virtual machine. You then assign Azure roles to this managed identity, such as storage blob data reader on a specific storage account. When your application code runs on the virtual machine, it requests a token from the Azure Instance Metadata Service at a well-known local endpoint. The metadata service authenticates the request using the virtual machine's managed identity and requests a token from Azure AD. Azure AD issues a token and returns it to the metadata service, which passes it to your application. Your application then uses this token to access the storage account. The token is valid for a limited time, and your application can request new tokens as needed. There are two types of managed identities: system-assigned and user-assigned. A system-assigned managed identity is created by enabling managed identity on an Azure resource. It exists only as long as that resource exists. When you delete the VM, the managed identity is automatically deleted. This tight lifecycle coupling is perfect for resources with dedicated purposes. You can have only one system-assigned managed identity per resource. A user-assigned managed identity is created as a standalone Azure resource. You create it explicitly, assign it roles, and then associate it with one or more Azure resources. Multiple resources can share the same user-assigned managed identity, which is useful when multiple applications need the same permissions. The identity exists independent of the resources using it, so deleting a virtual machine doesn't delete a user-assigned managed identity attached to it. You manage the identity's lifecycle separately. Use system-assigned identities when each resource needs unique permissions or when you want automatic cleanup. Use user-assigned identities when multiple resources share permissions, when you want to pre-configure access before deploying resources, or when you need the identity to persist beyond resource lifecycles. For most scenarios, system-assigned identities are simpler and preferred unless you have a specific reason to share identities. Practical CLI comparison. Let's make these concepts concrete by comparing how you perform common IAM tasks in both AWS and Azure using their command line interfaces. This will help you translate your AWS operational knowledge to Azure. The first example shows how to list all users. In AWS, you use the AWS IAM list users command. This returns JSON containing an array of IAM users in the current account. The output includes each user's username, ARN, user ID, creation date, and password last used timestamp. Remember, these are IAM users that exist only within this AWS account. In Azure, you use the AZAD user list command to list Azure AD users. The AZAD commands interact with Azure Active Directory, which is separate from resource management. The output shows users across your entire Azure AD tenant, not just one subscription. Each user has an object ID, user principal name, their email like login, display name, and other attributes. These are the same users regardless of which subscription you're working with. The second example demonstrates creating a group. In AWS, AWS IAM Create Group creates a group named Developers. This group exists only in the current AWS account. You would then attach policies to define what permissions members have. AWS groups are purely for organizing users and sharing policies. They have no other purpose. In Azure, Azure AD Group creates a group in Azure AD with a display name and a mail nickname. Azure AD groups have richer capabilities than AWS IAM groups. They can have mail-enabled features, support dynamic membership based on user attributes, and integrate with Microsoft 365 services. For Azure RBAC purposes, you'd create a security group and then assign it roles at various scopes. The third example shows role assignment, which is conceptually similar to attaching policies in AWS but works differently. In AWS, you might attach a managed policy to a user with AWS IAM attach user policy, specifying the username and policy ARN. This directly grants that user the permissions defined in the policy. You might also attach policies to groups or roles. Azure's approach is assignment-based rather than attachment-based. You use a Z-role assignment create to assign a role to a principal user, group, or service principal at a specific scope. The example assigns the contributor role to a user at the subscription level. You specify who gets access the assignee, identified by object ID, what they can do the role, and where they can do it the scope. This assignment automatically grants permissions to all resources within that subscription due to scope inheritance. The fourth example demonstrates creating an application identity. In AWS, you might create an IAM user for an application, though best practice is to use roles when possible. The example shows creating a user named AppService and creating an access key for it. The access key ID and secret access key are returned once, and you must store them securely and configure your application with them. In Azure, you create a service principal using a zadd create for RBAC. This command creates a service principal in Azure AD, generates credentials, and optionally assigns it a route at a specified scope. For example, this creates a service principal named myAppServicePrincipal with the contributor role at a subscription level. The output includes the service principal's application ID, display name, password also known as client secret, and tenant ID. You would provide these to your application for authentication. However, for applications running in Azure, using managed identities is preferred over service principals with explicit credentials. These examples illustrate the philosophical differences. AWS IAM commands focus on account-scoped identity and policy management, while Azure separates identity management, AZ, AD commands, from authorization, AZ role assignment commands. AWS uses attachment semantics, attach a policy to a user, while Azure uses assignment semantics, assign a role to a principal at a scope. Understanding these patterns will help you navigate Azure's IAM system effectively. Conditional Access Policies. Azure Conditional Access is a powerful capability that has no direct equivalent in AWS IAM. It allows you to enforce access controls based on signals like user location, device state, application being accessed, and real-time risk detection. This is fundamentally different from AWS IAM's static policy evaluation, which makes decisions based only on who the identity is and what resource they're accessing. Think of conditional access as an intelligent gatekeeper that sits between Azure AD authentication and resource access. After a user proves their identity with a password or other credentials, conditional access evaluates a set of conditions before allowing them through. These conditions can include whether they're connecting from a trusted network, whether their device is compliant with your organization's policies, whether they're using a managed application, and whether Azure AD Identity Protection has detected risky behavior. The power of conditional access comes from its ability to make context-aware decisions. For example, you might allow employees to access resources without additional authentication when they're in the office, but require multi-factor authentication when they're working from home. You could block access entirely from certain countries where your organization doesn't operate. You could require that sensitive financial applications only be accessed from corporate-managed devices that meet security requirements. The diagram on the slide shows how conditional access works in the authentication flow. A user starts by attempting to sign into Azure AD. Azure AD authenticates their credentials through whatever method is configured, such as password, passwordless authentication, or federated authentication with an on-premises Active Directory. Once authentication succeeds, conditional access policies are evaluated before granting access. Conditional access checks several signals. The user location signal determines whether they're connecting from a trusted network or location. Device compliance checks if the device meets your organization's security requirements, such as having encryption enabled, being up to date with patches, and running approved software. The application signal identifies what resource they're trying to access, allowing different policies for different applications. Risk detection uses Azure AD Identity Protection to identify suspicious behavior like impossible travel, sign-ins from anonymous IP addresses, or password spray attacks. Based on these signals and your configured policies, conditional access makes a decision. It might grant access immediately if all conditions are met. It might require additional authentication through multi-factor authentication, even if the user has already provided a password. It might block access entirely if the risk is too high or the conditions aren't met. It might grant access but only to web applications, not native apps, or only with limited permissions. AWS doesn't have a built-in equivalent to conditional access. In AWS, you would need to implement similar functionality through a combination of AWS IAM policy conditions, integration with third-party identity providers that support adaptive authentication, AWS WAF for network-based controls, and custom application logic. Azure's conditional access provides this capability natively and applies consistently across all Azure AD integrated applications. Privileged Identity Management. Azure Privileged Identity Management, commonly called PIN, is Azure's solution for just-in-time privileged access. It addresses a fundamental security principle. Users shouldn't have standing administrative access to sensitive resources. Instead, they should elevate their privileges only when needed, for a limited time, with approval and audit trails. AWS has no native equivalent to PIN. You would need to build this using AWS Lambda, step functions, and IAM role switching. The problem with traditional role assignments in Azure is that they're persistent. If you assign someone the owner role on a subscription, they have those powerful permissions continuously, 24 hours a day, 7 days a week, whether they need them or not. This creates security risk. If their account is compromised, the attacker has immediate administrative access. If the user makes a mistake, they have the permissions to cause significant damage. PIM solves this by making high-privilege role assignments eligible rather than active. With PIM, you designate a user as eligible for a role rather than directly assigning it. The user doesn't have the role's permissions until they activate it. To activate, they submit a request through the Azure portal, providing justification for why they need elevated access. Depending on your configuration, the request might be automatically approved, or it might require approval from designated administrators. Once approved, the user has the role's permissions for a time-limited period, typically a few hours. After the time expires, their privileges automatically expire, and they return to their normal permission level. Let's walk through the sequence diagram showing the PIM activation workflow. An administrator starts by configuring PIM for a role, such as the owner role on a production subscription. They designate which users are eligible for this role and set activation requirements. These requirements might include requiring justification, requiring approval, requiring multi-factor authentication at activation time, or any combination of these. When a user needs elevated access, they go to the PIM portal and request activation of their eligible role. They provide justification explaining why they need this access, such as, need to modify production network configuration for incident response. If approval is required, PIM notifies the designated approvers. An approver reviews the request, checks the justification, and can approve or deny it. If the request doesn't require approval, or once it's approved, PIM activates the role assignment for the specified duration, such as 8 hours. During this active period, the user has all the permissions of that role. They can perform administrative tasks, make configuration changes, access sensitive data, or whatever the role allows. Azure logs all actions taken during this elevated access period. When the time limit expires, PIM automatically deactivates the role assignment. The user's permissions return to their baseline level. If they need elevated access again, they must submit a new activation request. PIM provides comprehensive audit capabilities. You can see who activated which roles, when they activated them, how long they held elevated access, what justification they provided, and who approved the requests. This creates a complete audit trail for compliance purposes. PIM also sends notifications when users activate roles, when activations are about to expire, and when critical roles are used, keeping administrators informed of privileged access usage. PIM supports both Azure resource roles like owner and contributor, and Azure AD directory roles like global administrator and user administrator. This means you can use the same just-in-time access model for both managing Azure infrastructure and managing your Azure AD tenant. PIM also supports role activation through Azure CLI and PowerShell, allowing you to integrate just-in-time access into automated workflows and scripts. Azure Policy versus AWS Organizations. Azure Policy and AWS Organizations service control policies serve similar purposes but work quite differently. Both allow you to enforce governance rules across your cloud environment, but Azure Policy is more feature-rich and flexible in many ways. AWS Organizations service control policies are deny-based policies that set permission boundaries. They define the maximum permissions available to accounts within an organizational unit. An service control policy can prevent accounts from using certain services or performing certain actions, but it cannot grant permissions. Think of service control policies as guardrails that prevent certain actions regardless of what IAM policies allow. If an service control policy denies access to S3, no IAM policy within that account can grant S3 access. Azure Policy takes a different approach with more capabilities. Azure policies can audit resources for compliance, deny non-compliant resource creation or modifications, automatically modify resources to bring them into compliance, or automatically deploy resources alongside other resources. This makes Azure Policy both a guardrail and an active compliance tool. The table on the slide compares key aspects. For policy enforcement, AWS service control policies use a deny-only model, while Azure Policy supports deny, audit, modify, append, and deploy if not exists effects. This means Azure Policy can not only prevent bad configurations but also fix them automatically. AWS organizations cannot automatically remediate non-compliance, while Azure Policy can deploy or modify resources to achieve compliance. Regarding scope granularity, AWS SCPs apply at the organizational unit or account level. Azure policies can apply at management group, subscription, resource group, or even individual resource level. This finer granularity allows more targeted governance. For inheritance, both AWS SCPs and Azure policies inherit down the hierarchy, but Azure's inheritance goes all the way to individual resources. Azure Policy includes built-in policy definitions for common governance requirements. For example, there's a built-in policy to require secure sockets layer connections to storage accounts, to audit virtual machines that don't have disaster recovery enabled, to deny creation of public IP addresses, or to require specific tags on resources. You can also create custom policies using JSON definitions. A powerful feature unique to Azure Policy is policy initiatives, which are collections of policies grouped together. For example, the Azure Security Center initiative includes over 100 individual policies that audit security configurations across your environment. You assign the initiative once, and all its policies are applied together. This simplifies governance by letting you implement comprehensive compliance frameworks like CIS benchmarks or PCI DSS requirements with a single assignment. Azure Policy also integrates with Azure Blueprints, which are packages that can include policy assignments, role assignments, ARM templates, and resource groups. Blueprints let you define a repeatable set of Azure resources and policies that implement your organization's standards. This is similar to AWS Service Catalog but with tighter integration into the governance model. Cross-tenant access and B2B. One area where Azure significantly differs from AWS is in handling cross-organizational collaboration. Azure's business-to-business capabilities, built into Azure AD, make it remarkably easy to grant external users access to your resources without creating separate accounts or managing external credentials. In AWS, cross-account access requires establishing trust relationships and using role assumption. If you want to grant a user from another organization access to your AWS account, you have a few options. Create an IAM user in your account for them, which means you're managing their credentials. Use IAM roles with trust policies allowing their account to assume roles in yours, which requires coordination and still needs them to switch roles. Or federate through a third-party identity provider that both organizations trust. Azure takes a simpler approach through Azure AD B2B collaboration. You can invite external users to your Azure AD tenant as guest users. These guests authenticate using their home organization's credentials, whether that's another Azure AD tenant, a Microsoft account, Google account, or other supported identity providers. Once invited and accepted, the guest user appears in your Azure AD and can be assigned roles just like internal users, but they continue to authenticate with their home identity provider. The diagram illustrates how B2B collaboration works. Company A has an Azure AD tenant with their internal users. Company B also has their own Azure AD tenant. A user from Company B needs access to resources in Company A's subscription. An administrator from Company A sends a B2B invitation to the Company B user's email address. The Company B user receives the invitation email and accepts it. Azure AD creates a guest user object in Company A's tenant, but this object points back to the user's identity in Company B's tenant. The administrator at Company A can now assign Azure roles to this guest user, such as contributor on a specific resource group or reader on a subscription. When the guest user accesses resources, they sign in using their Company B credentials. Company B's Azure AD authenticates them and passes a token to Company A's tenant, which then authorizes access based on the role assignments. This creates a seamless collaboration experience. The Company B user doesn't need to remember different credentials for Company A's environment. Company A doesn't need to manage the user's password, multi-factor authentication, or account lifecycle. If the user leaves Company B, their access to Company A's resources automatically ends when Company B disables their account. This delegation of identity management is powerful for security and operational efficiency. Azure AD B2B also supports bulk invitations, allowing you to invite many external users at once from a CSV file. It supports access reviews, letting you periodically review which external users have access and remove those who no longer need it. It provides detailed audit logs of guest user activity. You can use conditional access policies to apply additional requirements to guest users, such as requiring them to use multi-factor authentication or restricting which applications they can access. For scenarios requiring even tighter integration between organizations, Azure AD supports B2B Direct Connect for teams and cross-tenant access policies that allow configuring trust relationships between tenants with fine-grained control over what can be accessed. Application registration and API permissions. When you develop applications that need to access Azure resources or Microsoft APIs, you register them in Azure AD and define their required permissions. This process differs significantly from AWS IAM's approach to application access and introduces concepts like delegated permissions and application permissions that do not exist in AWS. In AWS, an application typically uses IAM users with access keys, or on EC2, assumes an IAM role through instance profiles. The permissions are defined in IAM policies attached to that user or role. There's no distinction between permissions granted on behalf of a user versus permissions granted directly to the application. Azure introduces this distinction through its application registration and consent model. When you register an application in Azure AD, you create an application object that defines the application's identity and required permissions. This registration includes details like the application's name, redirect URLs for authentication flows, and most importantly, the API permissions the application needs. API permissions come in two types: delegated permissions and application permissions. Delegated permissions are used when the application acts on behalf of a signed-in user. The effective permissions are the intersection of what the application is allowed to do and what the signed-in user is allowed to do. For example, if an application has delegated permission to read files, but the signed-in user only has access to certain folders, the application can only read files in those folders when acting on behalf of that user. Application permissions are used when the application runs without a signed-in user, such as a background service or daemon. These permissions grant the application direct access to resources regardless of any user context. For example, an application with application permission to read all users in the directory can read all users, not limited to any individual user's permissions. This is similar to an AWS IAM role for an application, but with finer-grained control. The diagram shows the complete application registration and consent workflow. A developer starts by registering an application in Azure AD through the Azure portal or API. They specify what API permissions the application needs, selecting from Microsoft Graph permissions for accessing Microsoft 365 data, Azure Management API permissions for managing Azure resources, or permissions for custom APIs their organization has registered. For sensitive permissions, an administrator must grant consent before the application can use those permissions. This consent represents the administrator explicitly approving the application to access resources with these permissions. For less sensitive permissions, users might grant consent themselves when they first sign into the application. Once consent is granted, Azure AD issues access tokens to the application that include the approved permissions. When the application needs to access a resource, it presents its access token. Azure AD validates the token and checks that it contains the necessary permissions for the requested operation. If the token is valid and contains appropriate permissions, the application can access the resource. This token-based approach provides fine-grained control and audit capabilities. You can see which applications have accessed which resources and revoke access by revoking consent. The consent model provides security benefits. Users can see exactly what permissions an application is requesting before they grant access. Administrators can control which applications can be used in the organization and what permissions they can have. Azure AD can track all consent grants and access patterns, providing visibility into application access that's difficult to achieve in AWS without custom implementation. Identity protection and risk-based access. Azure AD Identity Protection provides automated threat detection and risk-based conditional access that goes far beyond anything available in AWS IAM. It continuously analyzes sign-in behavior and user activity to detect anomalies and suspicious patterns, then can automatically respond to protect your organization. AWS IAM. has no built-in threat detection or risk-based access controls. You would need to implement this through CloudTrail log analysis, integration with third-party security information and event management systems, and custom Lambda functions to detect and respond to suspicious activity. Azure provides this capability natively through identity protection. Identity protection detects several types of risky sign-ins and risky users. Risky sign-ins are individual authentication attempts that might not have been performed by the legitimate user. These include sign-ins from anonymous IP addresses such as Tor exit nodes, sign-ins from locations the user hasn't signed in from before with unusual characteristics, sign-ins from IP addresses that Microsoft has associated with malicious activity, impossible travel scenarios where a user appears to sign in from two distant locations within a timeframe that's physically impossible, password spray attacks where an attacker tries common passwords across many accounts, and sign-ins with unusual patterns like signing in at unusual times or with unusual applications. Risky users are accounts that have been compromised or show patterns indicating compromise. These include users whose credentials have been leaked in data breaches that Microsoft monitors, users exhibiting multiple risky behaviors over time, and users flagged by administrators as compromised. Identity protection assigns risk levels from low to high based on the severity and confidence of the detection. The real power comes from integrating identity protection with conditional access policies. You can create policies that automatically respond to detected risks. For example, a policy might require multi-factor authentication for medium-risk sign-ins, forcing the user to prove their identity with a second factor before granting access. For high-risk sign-ins, the policy might block access entirely until an administrator investigates. For risky users, you might require password reset before allowing access, ensuring the account is secured even if credentials were compromised. The table on the slide shows common risk detections. Atypical travel detects when a user signs in from an unusual location compared to their historical patterns. Anonymous IP address identifies sign-ins from known anonymous services like VPNs and Tor. Leaked credentials alerts when Microsoft's threat intelligence identifies user credentials in breach databases on the dark web. Malware-linked IP address detects sign-ins from IP addresses known to communicate with malware command and control servers. Unfamiliar sign-in properties identifies characteristics that don't match the user's typical sign-in patterns. Identity protection also provides reporting and investigation tools. The Risky Users report shows accounts flagged as risky with details about why they're risky. The Risk Detections report provides granular details about individual risk events. The Risky Sign-ins report shows authentication attempts that were flagged as risky. Administrators can investigate these reports, confirm whether activity was legitimate or malicious, and take action like requiring password reset or confirming account compromise. Risk events can be automatically remediated or require administrator action depending on your policies. If a user successfully completes multi-factor authentication in response to a risky sign-in, identity protection can automatically dismiss the risk detection, treating the successful MFA as proof of legitimate access. If an administrator confirms a sign-in was legitimate, the risk is dismissed. If confirmed as compromised, all active sessions are revoked and the account is secured. This risk-based approach represents a significant security advancement over traditional static access controls. Instead of only checking who someone is and what they're allowed to do, Azure can also evaluate how suspicious their current activity appears and adjust access requirements accordingly. This adaptive security posture is increasingly important as attacks become more sophisticated. Resource locks and protection. Azure provides resource locks as a protection mechanism against accidental deletion or modification of critical resources. This capability operates at a different level than RBAC permissions and provides an additional safety layer that AWS doesn't natively offer in the same way. In AWS, you can prevent deletion through various mechanisms like termination protection on EC2 instances, MFA delete on S3 buckets, stack policies in CloudFormation, and deletion policy attributes in templates. However, these protections are service-specific and don't provide a unified protection mechanism across all resource types. Each service implements deletion protection differently, requiring you to understand and configure multiple mechanisms. Azure Resource Locks provide a consistent protection mechanism that works the same way across all resource types. There are two types of locks: cannot delete and read-only. A cannot delete lock prevents deletion of the resource but allows modifications. A read-only lock prevents both deletion and any modifications to the resource. These locks apply regardless of RBAC permissions. Even if you have owner role on a resource, you cannot delete it if a cannot delete lock is applied. This creates a separate authorization layer specifically for protecting resources. The diagram illustrates the lock inheritance hierarchy in Azure. Locks can be applied at any scope: management group, subscription, resource group, or individual resource. Like RBAC permissions, locks inherit down the hierarchy. If you apply a cannot delete lock at a resource group level, all resources within that resource group are protected from deletion, even if they don't have individual locks. If you apply a read-only lock at a subscription level, all resource groups and resources in that subscription become read-only. In the example shown, an administrator applies a cannot delete lock at the subscription level. This lock automatically inherits down to resource group A and resource group B. All resources within these resource groups are protected from deletion. The lock appears on Virtual Machine 1, Storage Account 1, Virtual Machine 2, and SQL Database 1. None of these resources can be deleted by anyone, regardless of their RBAC permissions, unless the lock is first removed. This inheritance behavior makes locks powerful for protecting entire environments. If you have a production subscription, you might apply a cannot delete lock at the subscription level to protect all production resources. Developers and operators can still modify resources, deploy updates, and perform their work, but they cannot accidentally delete critical infrastructure. This is especially valuable in preventing mistakes during automation or scripting, where a single command could delete multiple resources. To delete a locked resource, you must first remove the lock, which requires specific permissions. The lock removal operation is separate from the resource deletion operation, creating a two-step process that prevents accidental deletion. This two-step process also appears in audit logs, providing clear visibility when someone removes protection from a resource. You can set up alarms to notify administrators whenever a lock is removed, allowing you to monitor protection changes. Resource locks interact with our RBAC in important ways. To create or delete locks, you need the Microsoft.authorization/locks/ permission, which is included in the owner and user access administrator roles but not in contributor. This means someone with contributor access can manage resources but cannot remove locks protecting those resources. This separation of duties is valuable for security. Operational teams can have contributor access to work with resources, while only security teams with owner access can modify protection mechanisms. Locks are particularly useful for protecting resources that support other resources. For example, you might lock the VNet that supports your production applications, the resource group containing your hub networking components, or the storage account that holds your backup data. Even if someone accidentally tries to delete these resources or an automation script targets them, the lock prevents the deletion and the infrastructure remains intact. Custom roles and permission actions. While Azure provides hundreds of built-in roles, sometimes you need custom roles tailored to your organization's specific requirements. Creating custom roles requires understanding Azure's permission model and the granular actions available for each resource provider. Azure's permission model is based on resource provider operations. Every action you can take in Azure, whether creating a virtual machine, reading a storage account, or modifying a network security group, corresponds to an operation in a resource provider. These operations follow a naming pattern: resource provider, resource type, action. For example, Microsoft.compute/virtual machines/start/action represents the operation to start a virtual machine in the compute resource provider. When creating a custom role, you specify which operations to include in the actions array, which operations to exclude in the not actions array, which data operations to include in data actions, and which data operations to exclude in not data actions. The distinction between actions and data actions is important. Actions control management plane operations like creating or deleting resources. Data actions control data plane operations like reading or writing data within resources. The code example on the slide shows a custom role definition for a virtual machine operator. This role allows reading virtual machine information through Microsoft.compute/virtual-machines/read, starting virtual machines through Microsoft.compute/virtual-machines/start/action, restarting them through Microsoft.compute/virtual-machines/restart/action, and deallocating them through Microsoft.compute/virtual-machines/deallocate/action. The not actions array explicitly excludes Microsoft.compute/virtual-machines/delete, preventing deletion even though other management operations are allowed. The assignable scopes define where this custom role can be assigned. In the example, it's limited to a specific subscription. You could make it assignable at a management group level to use across multiple subscriptions, or restrict it to a single resource group. Limiting assignable scopes is a security best practice that prevents the role from being used in unintended contexts. To discover what operations are available for a resource provider, you use the Azure Command Line Interface or PowerShell to list operations. The command AZ provider operation show Microsoft.compute displays all operations available for the compute resource provider. This includes operations for virtual machines, disks, availability sets, and other compute resources. Each operation has a description explaining what it does, helping you understand what permissions you're granting. When designing custom roles, start with a built-in role that's close to what you need and modify it. You can export a built-in role definition to JSON, edit it to add or remove operations, give it a new name and description, and create your custom role from the modified definition. This is easier than starting from scratch and ensures you don't miss important operations. Consider using wildcards carefully in custom roles. You can specify Microsoft.compute/virtual-machines/* to grant all operations on virtual machines. While convenient, this includes future operations that Microsoft might add to the resource provider, potentially granting more permissions than intended. For highly privileged custom roles, explicitly list operations rather than using wildcards. Document your custom roles thoroughly. Include the role's purpose, who requested it, why built-in roles were insufficient, and what permissions it grants. Store role definitions in source control so you can track changes over time. Review custom roles periodically to ensure they still meet requirements and haven't become overprivileged. As Azure adds new capabilities and built-in roles, you might find that a custom role is no longer necessary because a new built-in role now covers the use case. Federated Identity and External IDP. Both AWS and Azure support federated identity, allowing users to authenticate with external identity providers instead of creating separate cloud credentials. However, Azure's federation capabilities through Azure AD are more comprehensive and integrated than AWS's federation through IAM and Cognito. In AWS, federation typically works through one of several mechanisms. You can use SAML 2.0 federation where your identity provider issues SAML assertions that AWS STS exchanges for temporary security credentials. You can use Web Identity Federation with providers like Amazon, Facebook, or Google for consumer applications. You can use Custom Federation where you write code to authenticate users and call STS to issue temporary credentials. You can use AWS Single Sign-On, now called IAM Identity Center, which provides a more managed federation experience. Azure AD provides federation capabilities built into the core identity platform. Azure AD supports multiple federation protocols. SAM L2.0 for traditional enterprise federation. OAuth 2.0 and OpenID Connect for modern application integration, and WS Federation for older Microsoft applications. This multi-protocol support means you can integrate with virtually any identity provider. The most common federation scenario is connecting Azure AD with an on-premises Active Directory. Many organizations have invested heavily in Active Directory for managing user identities, group memberships, and access policies. Rather than recreating this in the cloud, you can federate your on-premises AD with Azure AD. This allows employees to use their existing AD credentials to access Azure resources and Microsoft 365 services without creating separate cloud accounts. The diagram shows the federation authentication flow. A user attempts to access an Azure resource. Azure AD redirects them to the configured external identity provider, which could be an on-premises Active Directory Federation Services, Okta, Ping Identity, or any SAML-compliant identity provider. The user authenticates with their external IDP using whatever method that provider supports, such as password, smart card, or biometric authentication. The external identity provider validates the user's credentials and issues an authentication token or SAML assertion containing claims about the user. These claims might include their username, email address, group memberships, and other attributes. The external identity provider redirects the user back to Azure AD with this token. Azure AD validates the token, verifying it came from a trusted identity provider and hasn't been tampered with. If the token is valid, Azure AD issues its own token for the user, which includes their Azure AD Object ID and other Azure-specific information. The user is now authenticated to Azure AD through their external identity, and Azure RBAC evaluates their permissions based on role assignments in Azure. The key benefit is that the user's password never goes to Azure AD. Authentication happens at the external identity provider using whatever security measures that provider implements. If the external IDP requires multi-factor authentication, password rotation, or other security controls, those apply without Azure AD needing to know about them. Azure AD also supports advanced federation scenarios like home realm discovery, where Azure AD automatically redirects users to the correct identity provider based on their email domain. Multiple identity providers can be configured, allowing different user populations to authenticate with different systems. Conditional access policies can apply to federated users just like cloud-only users, adding additional requirements based on risk or context. For organizations using multiple cloud providers, Azure AD can act as the identity provider for other services. You can configure AWS to federate with Azure AD, allowing users to sign in to AWS with their Azure AD credentials. This creates a unified identity experience across clouds, with Azure AD serving as the central identity authority. The same approach works with other SaaS applications, creating single sign-on across thousands of applications through Azure AD's pre-integrated application gallery. Comparing IAM best practices. Let's conclude this section by comparing best practices for IAM in AWS versus Azure. While the underlying principles of least privilege, defense in depth, and separation of duties apply to both platforms, the implementation approaches differ due to architectural differences. For identity management, AWS best practice is to avoid using the root account for daily operations and instead create individual IAM users with appropriate permissions. Enable MFA for all users, especially those with administrative access. Use IAM roles instead of IAM users for applications. Rotate access keys regularly if you must use them. In Azure, best practice is different because of the centralized Azure AD model. Enable Azure AD multi-factor authentication for all users, but especially administrators. Use managed identities for applications instead of service principals with secrets. Implement Azure AD Privileged Identity Management for just-in-time administrative access. Use Azure AD Identity Protection for risk-based access controls. For permission assignment, AWS recommends granting least privilege by starting with minimal permissions and adding more only as needed. Use AWS managed policies when they fit your requirements. Create custom policies for specific use cases. Use IAM permission boundaries to delegate permission management safely. Regularly review permissions using IAM Access Analyzer. Azure takes a similar approach but with role-based emphasis. Assign roles at the appropriate scope, not broader than necessary. Use built-in roles when possible instead of custom roles. Assign roles to groups rather than individual users for easier management. Use Azure Policy to enforce governance rules across subscriptions. Conduct regular access reviews to ensure permissions remain appropriate. For cross-account or cross-subscription access, AWS recommends using roles with trust policies rather than creating IAM users in multiple accounts. Use AWS organizations to manage multiple accounts centrally. Implement service control policies to set permission boundaries at the organization level. Azure's approach is simpler due to centralized identity. Use Azure AD groups with role assignments across subscriptions. Implement management groups for organizational hierarchy. Use Azure Policy at management group level for consistent governance. For external collaboration, use Azure AD B2B instead of creating internal accounts. The table provides a comprehensive comparison. For identity creation, AWS suggests minimizing IAM users, while Azure suggests using Azure AD as a single identity source. For application credentials, AWS recommends IAM roles with instance profiles, while Azure recommends managed identities with automatic credential management. For privileged access, AWS suggests careful role assumption with session duration limits, while Azure recommends PIM with time-based activation and approval workflows. Regarding audit and compliance, AWS relies on CloudTrail for logging API calls and IAM Access Analyzer for permission analysis. Azure provides Azure Activity Logs for resource operations and detailed Azure AD sign-in logs and audit logs for identity activities. Azure's audit logs are more comprehensive for identity operations because Azure AD tracks authentication events, MFA usage, risky sign-ins, and conditional access decisions in detail. For automation, AWS recommends using infrastructure as a service with CloudFormation or Terraform, implementing IAM policies through code rather than manual configuration. Azure similarly recommends ARM templates or Terraform, but also emphasizes Azure Policy for continuous compliance enforcement. Azure's declarative policy model allows you to define desired state and have Azure continuously audit and enforce compliance. Both platforms emphasize the importance of regular reviews. In AWS, use AWS IAM Access Analyzer to identify unused permissions, review CloudTrail logs for unusual activity, and periodically audit IAM policies for over-permissive rules. In Azure, implement Azure AD Access reviews for periodic certification of access, monitor identity protection for security alerts, review PIM activation patterns for unusual administrative access, and audit conditional access policy effectiveness. Azure AD Administrative Units. Azure AD Administrative Units provide a way to delegate administrative permissions to a subset of users within your Azure AD tenant. This is a capability that doesn't have a direct equivalent in AWS IAM, as AWS IAM doesn't support delegated administration within a single account in the same way. In large organizations, you might have thousands of users across multiple departments, regions, or business units. Without administrative units, when you assign someone a directory route lead like user administrator, they can manage all users in the entire tenant. This violates the principle of least privilege if they only need to manage users in their department or region. Administrative units solve this by allowing you to scope directory route assignments to a container of users, groups, or devices. Think of administrative units as organizational containers within Azure AD. You create an administrative unit, add members to it such as users from the marketing department or devices in the London office, and then assign directory roles scoped to that administrative unit. Delegated versus application permissions. Understanding the difference between delegated permissions and application permissions is fundamental to working with Azure AD applications and APIs. This concept doesn't have a direct parallel in AWS IAM, where permissions are generally service to service without the same user context distinction. The difference becomes critical when you're building applications that integrate with Microsoft Graph, Azure Services, or custom APIs protected by Azure AD. Delegated permissions are used when your application acts on behalf of a signed-in user. The application can only access resources that the user themselves could access, limited by the permissions granted to the application. Think of this as the application borrowing the user's identity to perform actions. Even if the application has been granted broad delegated permissions, it can only access data the current user has rights to access. For example, consider a mobile email application that uses the Microsoft Graph API. When you grant it the mail.read delegated permission, the app can read your email when you're signed in. But it can only read your email, not other users' email, even though the mail.read permission exists. The delegated permission works within the context and boundaries of the authenticated user's own permissions. Application permissions allow an app to access resources using its own identity, without a signed-in user. The application acts as itself, not on behalf of anyone. This is used for background services, daemons, or automated processes that run without user interaction. When you grant an application the mail.read.all application permission, it can read email for all users in your organization, because it's operating with its own authority, not borrowing a user's identity. The diagram shows how these permission types work in practice. For delegated permissions, a user signs into the application, which requests a token from Azure AD. The token includes both the application's identity and the user's identity. When the app calls an API using this token, the API checks both the permission granted to the app and what the user is allowed to access. The effective permission is the intersection of what the app can do and what the user can do. For application permissions, there's no user sign-in. The application authenticates to Azure AD using its client credentials, a secret, certificate, or federated credential. Azure AD issues a token that represents only the application's identity. When the app calls an API with this token, the API checks only the application's permissions. The app can access anything its application permissions allow, regardless of any individual user's rights. This distinction is important for security and compliance. Delegated permissions are generally safer because they're constrained by user permissions. Even if an application is compromised, an attacker can only access what the signed-in user could access. Application permissions are more powerful and risky if an application with broad application permissions is compromised. An attacker could access all data the application has permission to access across the entire organization. Admin consent requirements differ between these permission types. Many delegated permissions can be consented to by individual users. The first time they use an application, they see a consent prompt asking if they allow the app to access their data. Application permissions always require administrator consent because they grant organization-wide access. Users cannot consent to application permissions, ensuring that only administrators can grant this level of access. OAuth 2.0 and OpenID Connect flows. Azure AD's authentication is built on industry-standard OAuth 2.0 and OpenID Connect protocols. Understanding these flows is essential for integrating applications with Azure AD, and it represents a significant difference from AWS IAM, which uses signature-based authentication. While AWS SDK handles signing requests with access keys, Azure applications use token-based authentication with different flows for different scenarios. OAuth 2.0 is an authorization framework that enables applications to obtain limited access to user accounts. OpenID Connect is an identity layer built on top of OAuth 2.0 that adds user authentication. Together, they provide a complete framework for both authenticating users and authorizing access to protected resources. Azure AD implements multiple OAuth 2.0 flows, each designed for different application types and security requirements. The authorization code flow is the most secure and recommended flow for web applications and mobile apps. The flow starts when the user clicks Sign in your application. Your app redirects the user to Azure AD's authorization endpoint with parameters including your application's client ID and the permissions you're requesting. The user signs in and consents to the permissions if needed. Azure AD then redirects back to your application with an authorization code in the URL. Your application's backend then exchanges this authorization code for an access token by calling Azure AD's token endpoint. This exchange happens server to server and includes your application's client secret or certificate, so the authorization code is useless to an attacker who might intercept it from the redirect URL. Azure AD validates your application's credentials and the authorization code, then returns an access token your app can use to call APIs, and optionally a refresh token to get new access tokens when the current one expires. The diagram shows the complete authorization code flow. The user starts by accessing the web application, which redirects them to Azure AD for authentication. Azure AD authenticates the user, shows consent prompts if needed, then redirects back to the application with an authorization code. The application's backend exchanges this code for tokens by calling the token endpoint with the code and the application's client credentials. Azure AD validates everything and returns an access token. The application then uses this access token to call protected APIs like Microsoft Graph or Azure Resource Manager. The client credentials flow is used for service-to-service authentication where there's no user involved. This is equivalent to how AWS services use IAM roles. The service authenticates as itself, not on behalf of a user. Your application sends its client ID and client secret or certificate directly to Azure AD's token endpoint. Azure AD validates the credentials and returns an access token representing the application's identity. This token can then be used to call APIs with the application permissions granted to the service principal. The implicit flow was designed for single-page applications that run entirely in the browser with no backend server. However, it's now considered less secure and has been largely replaced by the authorization code flow with PKCE, or Proof Key for Code Exchange. PKCE adds an additional security layer that makes the authorization code flow safe to use from public clients like single-page apps or mobile apps that can't securely store client secrets. The on behalf of flow is used when a middle-tier service needs to call another service on behalf of the user. For example, a web API that your application calls might need to call Microsoft Graph on behalf of the user who called your application. Your application gets a token representing the user, calls your web API with that token, and the web API then exchanges that token for a new token to call Microsoft Graph. This maintains the user's identity through the entire call chain. Refresh tokens enable long-lived access without requiring users to repeatedly sign in. When Azure AD issues an access token, it can also issue a refresh token. Access tokens are short-lived, typically valid for 1 hour. When the access token expires, your application uses the refresh token to request a new access token without user interaction. This provides a good balance between security and user experience. Tokens expire frequently to limit exposure if compromised, but users aren't constantly prompted to sign in. Token anatomy and validation. Access tokens in Azure AD are JSON Web Tokens, or JWTs, and understanding their structure is important for troubleshooting authentication issues and implementing custom authorization logic in your applications. Unlike AWS SIG v4 signatures which are computed for each request, Azure uses bearer tokens that are presented with API calls. These tokens contain claims that describe the identity and permissions of the caller. A JWT consists of 3 parts separated by periods. the header, the payload, and the signature. The header describes the token type and the algorithm used to sign it. The payload contains claims about the user or application, the permissions granted, when the token was issued, and when it expires. The signature is created by hashing the header and payload with a secret key, allowing recipients to verify the token hasn't been tampered with. The header typically includes the token type, which is always JWT for access tokens, and the signing algorithm, usually RS-256 for RSA with SHA-256. Azure AD uses asymmetric key cryptography to sign tokens. It signs them with a private key, and recipients verify the signature using the corresponding public key published at Azure AD's OpenID configuration endpoint. This allows any service to validate that a token was truly issued by Azure AD without needing access to the private signing key. The payload contains numerous claims that provide information about the token and the principal it represents. The issuer claim identifies Azure AD as the token issuer and includes your tenant ID. The audience claim specifies which resource this token is meant for. Tokens intended for Microsoft Graph can't be used to access Azure Resource Manager, for example. The subject claim identifies the user or application the token represents. The issued at and expiration claims define the token's validity period. The diagram shows the structure of a typical Azure AD access token. At the top level, you have the header identifying this as a JWT signed with RS-256. The payload contains identity claims like the user's object ID and username, permission claims like the roles or scopes granted, and metadata claims like the token's expiration time and intended audience. The signature at the bottom ensures integrity. If anyone modifies the header or payload, the signature verification will fail. The roles claim contains application permissions when using the client credentials flow. If your service principal has been granted the storage blob data contributor role on a storage account, the roles claim in the token will include an identifier for that role. Azure services validate these roles claims to authorize operations. The scope claim contains delegated permissions for user context tokens. If a user has granted your app permission to read their email, the scope claim will include mail.read. Azure AD includes additional claims for enhanced security and functionality. The authentication method reference claim describes how the user authenticated, whether they used a password, certificate, or MFA. The authentication time claim shows when the user last authenticated, useful for scenarios requiring recent authentication. The app ID claim identifies which application the token was issued to, preventing token misuse between different applications. When your API receives a token, it must validate several aspects before trusting it. First, verify the signature using Azure AD's public keys to ensure the token was really issued by Azure AD and hasn't been modified. Second, check the issuer claim to ensure it matches your expected Azure AD tenant. Third, verify the audience claim to ensure the token was meant for your API. Fourth, check the expiration claim to ensure the token hasn't expired. Only after all these validations pass should you trust the claims in the token. The not before claim specifies when the token becomes valid, usually the same as the issued at time. This prevents tokens from being used before they are supposed to be active. The token identifier is a unique ID for this specific token, useful for logging and debugging. If you need to revoke a user's access, you cannot revoke individual tokens. They remain valid until expiration. But you can revoke the refresh token, preventing new access tokens from being issued. Microsoft Graph API, the unified endpoint. Microsoft Graph is the unified API gateway for accessing data across Microsoft 365, Azure AD, Windows, and enterprise mobility and security. For AWS users, there isn't a direct equivalent. AWS services each have their own APIs. Microsoft Graph consolidates access to users, groups, mail, calendars, files, devices, and more through a single endpoint. Understanding Graph is essential because it's how you programmatically manage Azure AD and access Microsoft Cloud services. The Microsoft Graph API is exposed at a single base URL, https://graph.microsoft.com. All requests go through this endpoint, with different resource paths for different types of data. To read the current user's profile, you call get_on/me. To list all users in your organization, you call get_on/users. To access a user's email, you call get_on/me/messages. This consistent, RESTful design makes the API predictable and easy to work with. Every Microsoft Graph API call requires an access token with appropriate permissions. These are the delegated or application permissions we discussed earlier, scoped specifically to Microsoft Graph. When you register an application in Azure AD and configure its API permissions, you're selecting which Microsoft Graph permissions the application needs. Common permissions include user.read to read the signed-in user's profile, mail.send to send email on behalf of users, directory.read.all to read organization directory data, or files.read_write.all to access files in OneDrive and SharePoint. The diagram shows how applications interact with Microsoft Graph. Your application first authenticates to Azure AD and receives an access token with the permissions it needs. The application then makes REST API calls to Microsoft Graph, including the access token in the authorization header. Microsoft Graph validates the token, checks the permissions, and then accesses the underlying Microsoft service. Azure AD for user data, Exchange Online for mail, SharePoint for files, or Intune for device management. Microsoft Graph handles all the complexity of accessing these different services and presents a unified API to your application. Microsoft Graph uses OData conventions for querying, filtering, and pagination. You can use query parameters like filter to narrow results, select to specify which properties to return, order by to sort results, and top to limit the number of results. For example, to get the first 10 users sorted by display name, you would use get/users top = 10 and sign order by = display name. To find users in a specific department, get/users filter = department = operator engineering. Pagination is important when working with large result sets. If you request users and there are thousands in your organization, Microsoft Graph returns a page of results along with a next link property containing the URL to fetch the next page. You continue following these next links until there's no more data. This is similar to pagination in AWS APIs but uses OData's standardized approach rather than service-specific pagination tokens. Microsoft Graph supports batching, allowing you to combine multiple requests into a single HTTP call. This reduces network overhead when you need to perform several operations. You post to the /batch endpoint with a JSON payload containing multiple individual requests. Microsoft Graph processes them and returns all the responses together. This is useful for scenarios like creating multiple users, updating properties on several resources, or fetching data from different endpoints in a single round trip. Change notifications and webhooks in Microsoft Graph allow your application to subscribe to changes in resources. Instead of polling to check for updates, your app registers a webhook URL with Microsoft Graph for specific resources. When those resources change, Microsoft Graph sends a notification to your webhook. You might subscribe to changes in a user's mailbox to build a real-time email monitoring solution, or subscribe to changes in a specific SharePoint list to trigger workflows when items are added. The Graph SDKs for various programming languages provide strongly typed objects and methods for common operations. Instead of manually constructing REST calls, you use SDK methods like client.users.getOpen(close parenthesis) in Python or client.users.request(getAsync)(close parenthesis) in C#. The SDKs handle authentication, token refresh, retry logic, and error handling, making it much easier to build robust applications that integrate with Microsoft services. Hybrid identity with Azure AD Connect. Many organizations have existing on-premises Active Directory deployments and need to integrate them with Azure AD to enable hybrid cloud scenarios. Azure AD Connect is the tool that synchronizes identity data between on-premises AD and Azure AD, enabling users to access both on-premises and cloud resources with the same credentials. This concept doesn't have an equivalent in AWS, as AWS doesn't provide a directory synchronization service. Azure AD Connect runs on a server in your on-premises environment and periodically synchronizes user accounts, groups, and other objects from your on-premises Active Directory to Azure AD. The synchronization is one way by default from on-premises to cloud, meaning your on-premises AD remains the authoritative source for user information. When you create a user in on-premises AD, Azure AD Connect syncs that user to Azure AD within minutes, creating a corresponding cloud identity. The key benefit is single sign-on across on-premises and cloud resources. Users have one set of credentials that works everywhere. When they sign in to their Windows PC using their on-premises AD account, they're also automatically signed into Office 365, Azure Portal, and other Azure AD integrated applications. This provides a seamless experience while allowing you to maintain on-premises AD as your identity source of truth. The diagram illustrates the Azure AD Connect synchronization architecture. On-premises Active Directory contains your users, groups, and computers. Azure AD Connect synchronizes selected objects to Azure AD in the cloud. Users can then access both on-premises applications like file servers and SharePoint on-premises, as well as cloud applications like Office 365 and Azure services. The synchronization keeps the identities in sync, while authentication can happen either in the cloud or on-premises depending on your configuration. There are 3 authentication methods you can use with Azure AD Connect: password hash synchronization, pass-through authentication, and federation with ADFS. Password hash synchronization is the simplest and most commonly used method. Azure AD Connect synchronizes a hash of the user's password hash from on-premises AD to Azure AD. When users sign into cloud services, Azure AD can validate their credentials directly without contacting on-premises infrastructure. This provides the best user experience and resilience, as cloud authentication works even if on-premises infrastructure is down. Pass-through authentication validates credentials against on-premises Active Directory in real time. When a user signs into a cloud service, Azure AD sends the password validation request through an agent running on-premises. The agent validates the credentials against on-premises AD and returns the result to Azure AD. This ensures passwords never leave your on-premises environment, but requires on-premises infrastructure to be available for cloud sign-ins. Federation with Active Directory federation services provides the most control, but adds complexity. With federation, all authentication requests are redirected to your on-premises ADFS infrastructure. ADFS validates credentials and issues claims to Azure AD confirming the user's identity. This allows you to implement custom authentication policies, support smart cards or other advanced authentication methods, and maintain complete control over the authentication process. However, it requires deploying and maintaining a DFS infrastructure. Azure AD Connect synchronizes more than just users. It can sync groups, allowing you to manage group membership on-premises and have those groups available in Azure AD for assigning access to cloud resources. It can sync contacts for your global address list. It can sync device objects for hybrid Azure AD joint devices that are both domain joined to on-premises AD and registered in Azure AD. This comprehensive synchronization enables hybrid scenarios where resources and management span on-premises and cloud. Attribute filtering and scoping in Azure AD Connect control what gets synchronized. You can filter which organizational units to sync, exclude certain users or groups, or sync only users who meet specific criteria. Attribute transformations allow you to modify attributes during synchronization, such as constructing email addresses from multiple on-premises attributes or filtering sensitive data that shouldn't be synced to the cloud. Azure AD Domain Services. Azure AD Domain Services provides managed domain services like domain join, group policy, LDAP, and Kerberos authentication without requiring you to deploy, manage, and patch domain controllers in the cloud. This is useful for lift and shift scenarios where you're migrating applications to Azure that require traditional Active Directory features that Azure AD doesn't provide. AWS Directory Service offers similar functionality with its managed Microsoft AD offering. The key distinction is that Azure AD is a modern cloud identity service that doesn't provide all the features of on-premises Active Directory. Azure AD doesn't support LDAP binds, Kerberos authentication, computer accounts, or group policy objects. These are legacy features required by many on-premises applications. Azure AD Domain Services bridges this gap by providing a managed Active Directory domain in Azure that's compatible with these traditional requirements. When you enable Azure AD Domain Services, Azure creates a managed domain with 2 domain controllers deployed in your Azure Virtual Network. These domain controllers are fully managed by Microsoft. You don't patch them, backup them, or configure them directly. Azure AD automatically synchronizes user accounts and groups from your Azure AD tenant to this managed domain. If you're using Azure AD Connect to sync from on-premises AD, you get a complete sync chain: on-premises AD to Azure AD Domain Services. The diagram shows the relationship between these components. On-premises Active Directory syncs to Azure AD via Azure AD Connect. Azure AD Domain Services creates a managed domain that syncs users and groups from Azure AD. Virtual machines in Azure can domain join to this managed domain, enabling them to use group policy, Kerberos authentication, and LDAP queries just like they would with on-premises AD. Users can sign into these virtual machines with their Azure AD credentials, which are synchronized to the managed domain. Common use cases include migrating applications that require LDAP authentication, but you don't want to extend your on-premises AD to Azure. You enable Azure AD Domain Services, domain join your Azure virtual machines to the managed domain, and your applications can continue using LDAP without modification. Another scenario is enabling group policy for Azure virtual machines when you want centralized configuration management, but don't want to deploy and manage your own domain controllers in Azure. Password hash synchronization is required for Azure AD Domain Services. Even if you're using pass-through authentication or federation for Azure AD sign-ins, you must enable password hash sync to Azure AD, because Azure AD Domain Services needs these password hashes to validate Kerberos and NTLM authentication requests. This is an important consideration if your security policies prohibit syncing password hashes to the cloud. The managed domain has limitations compared to a full Active Directory forest. You don't have domain administrator access. Microsoft manages the domain infrastructure. You can't extend the schema, modify certain domain-level settings, or access the domain controllers directly. However, you can create organizational units, manage group policies within those OUs, and perform standard domain administrative tasks like creating groups and managing group membership. For AWS users familiar with AWS Directory Service Managed Microsoft AD, Azure AD Domain Services is quite similar. Both provide managed domain controllers in the cloud, support domain join and group policy, and integrate with cloud directory services for identity synchronization. The key difference is Azure AD Domain Services' tight integration with Azure AD, automatically syncing users and groups without additional configuration. Access reviews and governance. Access reviews in Azure AD provide automated governance workflows for periodically reviewing and certifying who has access to what resources. This addresses a common security challenge over time. Users accumulate permissions they no longer need, creating security risk. Access reviews ensure that access rights are periodically validated and unnecessary permissions are removed. AWS doesn't have a built-in equivalent feature, though you could build similar workflows using custom tooling around IAM policies. An access review is a time-bound campaign where reviewers are asked to confirm whether users or service principals still need their assigned access. You can create reviews for Azure AD role assignments, Azure Resource role assignments, group memberships, or application assignments. The review can be one-time or recurring, scheduled to run weekly, monthly, quarterly, or annually. When a review period begins, designated reviewers receive notifications and can approve or deny continued access for each principal. The diagram shows the access review workflow. An administrator creates an access review for a specific resource, role, or group, defining who the reviewers are and when the review should occur. When the review period starts, reviewers are notified and can see a list of users who have access. For each user, the reviewer decides whether to approve continued access or deny it, optionally adding justification. When the review completes, you can configure automatic actions, automatically remove access for denied users, or require manual intervention to process the results. Reviewers can be the resource owners, the users themselves performing self-review, specific designated individuals, or managers of the users being reviewed. For Azure AD admin roles, you might designate senior IT leadership as reviewers. For access to a specific SharePoint site, you might designate the site owner as the reviewer. Self-review is common for group memberships, where each quarter users confirm they still need membership in various groups. Access reviews integrate with privileged identity management for reviewing eligible role assignments. You can periodically review who has eligible access to privileged roles, ensuring that only users who need the ability to elevate their permissions maintain that access. This is particularly important for roles like Global Administrator or Owner on production subscriptions, where you want to ensure the list of eligible users is current and justified. Review history and audit logs capture all review decisions and actions. You can see who reviewed access, when they completed their review, what decisions they made, and whether access was actually removed. This audit trail is important for compliance requirements and security investigations. If a security incident involves a user with excessive permissions, you can review the access review history to see when that access was last validated and by whom. Automated remediation simplifies access governance. You can configure reviews to automatically remove access when a reviewer denies it, or when the review period ends and no one has approved continued access. For high-risk scenarios, you might configure reviews to automatically remove access if the review isn't completed within the specified timeframe, implementing a default deny approach. For less critical access, you might leave decisions manual, allowing administrators to review results before taking action. Recommendations in access reviews use sign in activity to suggest whether access should be continued. If a user hasn't signed into an application in the last 90 days, the review will recommend denying continued access. Reviewers can accept these recommendations or override them based on additional context. This machine-assisted review makes the process more efficient and helps identify obviously unused access that can be safely removed. Entitlement management and access packages. Entitlement management in Azure AD provides automated workflows for users to request access to resources they need. Instead of users emailing IT to request group memberships or application access, they can request access through a self-service portal. IT defines access packages that bundle together related resources, and users request access to these packages through an approval workflow. This is more sophisticated than anything built into AWS IAM, though some AWS customers build similar functionality using custom portals and automation. An access package is a collection of resources that users need to perform a job function or work on a project. It might include membership in several Azure AD groups, access to specific applications, assignment to Azure resource roles, and membership in SharePoint sites. For example, you might create a marketing department onboarding access package that grants new marketing team members access to all the tools and resources they need. Office 365 groups, the marketing SharePoint site, the marketing analytics application, and read access to the marketing resource group in Azure. The diagram illustrates the entitlement management flow. An administrator creates access packages defining what resources they contain and who can request them. Users discover available access packages through the My Access portal, where they can see packages they're eligible to request. When a user requests a package, the request goes through an approval workflow with designated approvers. If approved, the user is automatically granted all the resources in the package. Access can be time-limited, expiring after a defined period, or perpetual until removed. Security defaults and baseline protection. Security defaults in Azure AD provide baseline security protections that Microsoft recommends for all organizations, particularly those without dedicated security teams. When security defaults are enabled, Azure AD automatically enforces several security policies including required MFA for administrators, MFA challenges for users when necessary, blocking legacy authentication, and protecting privileged activities. This is a significant departure from AWS IAM, which doesn't enforce any security requirements by default. AWS provides recommendations but doesn't automatically enforce them. Security defaults are designed to be simple. They're either enabled or disabled for your entire tenant. When enabled, they immediately improve your security posture without requiring complex policy configuration. This makes them ideal for small organizations, startups, or anyone who wants strong security without the complexity of configuring individual conditional access policies. Larger organizations or those with complex requirements typically disable security defaults and implement custom conditional access policies instead. The specific protections that security defaults enforce include requiring all administrators to register for and use multi-factor authentication. Administrators must complete MFA every time they sign in. There are no exceptions. For regular users, security defaults require MFA registration and will challenge users for MFA when Azure AD determines the sign-in is risky, such as coming from a new location or unusual circumstances. This risk-based MFA for users provides protection without the overhead of requiring MFA for every single sign-in. The diagram shows how security defaults protect different aspects of authentication. At the top, all administrator sign-ins require multi-factor authentication every time, no matter where they are signing in from. For regular users, multi-factor authentication is required when risk is detected, unusual location, new device, or other suspicious indicators. Legacy authentication protocols like Population 3, SMTP, or basic authentication are completely blocked because they do not support multi-factor authentication, preventing attackers from bypassing multi-factor authentication by using these older protocols. Finally, certain privileged activities like accessing the Azure portal always require multi-factor authentication, even for non-administrator users. Legacy authentication blocking is particularly important because these older protocols cannot enforce multi-factor authentication. If you allow basic authentication from mail clients, attackers who compromise credentials can bypass multi-factor authentication by using these protocols. Security defaults protect against this by completely blocking these authentication methods. For organizations that truly need legacy authentication for specific scenarios, they must disable security defaults and use conditional access to implement more granular policies that might allow legacy auth from specific IP addresses while blocking it everywhere else. When you first create an Azure AD tenant, security defaults are automatically enabled. This ensures new organizations start with strong security. However, if your tenant existed before security defaults were introduced, they might be disabled, and you should consider enabling them. You can check and enable security defaults in the Azure AD portal under Properties, where you'll find a link to manage security defaults. Migration patterns from AWS IAM. Migrating identity and access management from AWS to Azure requires careful planning and understanding of the conceptual mappings between the platforms. While both provide comprehensive IAM capabilities, The architectural differences mean you can't simply translate AWS IAM policies one-to-one into Azure RBAC roles. This slide covers common migration patterns and strategies for organizations moving workloads from AWS to Azure or operating in both clouds. The first step is mapping your AWS identity structure to Azure. AWS IAM users typically map to Azure AD user accounts, but consider whether users should be cloud-only or synced from on-premises Active Directory. AWS IAM roles used by EC2 instances, Lambda functions, or other services map to Azure Managed Identities, which provide similar functionality with even less overhead. AWS IAM roles used for cross-account access or external federation map to Azure Service Principals, though the authentication mechanisms differ. For AWS IAM groups, you'll create equivalent Azure AD groups. However, Azure AD groups are more powerful. They can have dynamic membership based on user attributes, can be used for application access and licensing beyond just Azure Resource Access, and integrate with the broader Microsoft ecosystem. You might consolidate some AWS groups or restructure them to take advantage of Azure AD's capabilities. Consider using dynamic groups for automatic group population based on department, location, or other attributes. The diagram shows a typical migration pattern: delegated versus application permissions. Understanding the difference between delegated permissions and application permissions. OAuth 2. Token and Microsoft Hybrid Identity, Azure AD Access Entitlement, Security, Migration Patterns from AWS IAM. Migrating identity and access management from AWS to Azure requires careful planning and understanding of the conceptual mappings between the platforms.